So, as of all of you are familiar, we are into a big automotive transition now. You all may be well aware that India, not only India, in global level, there is a big push for reducing the global pollution, right? Global warming is one of the serious consequences, and every nation is making an effort to bring down the global warming. And one of the major contributor to the global warming is carbon dioxide that comes from industries, automotive sectors, and many other space sectors. Automotive sectors is also a contributing significantly to the greenhouse gases. So there is an interesting article which I mentioned here. Can lithium-ion batteries be the pinnacle of automotive applications? Renewable. This is published in Renewable News in 2016. You can go through this article. So as this article says, transportation is a. Hello, are you able to hear?
Yes, sir. Please carry on, sir.
Yes, sir. So, automotive transition, we are into a big automotive transition, and now transportation accounts to a single largest source of greenhouse gas emission, and there are about, it's expected to be about 500 plus million cars on the road. So, this article says, annual CO2 emission by a typical passenger vehicle. So, for every gallon of petrol or gasoline you burn, producing 8,887 grams of, means 411 grams per mile. So that much of CO2 you will be producing. So in average passenger cars, you use about 11,400 miles per year. So you will produce something like 4.7 metric tons of CO2 will be emitted to the atmosphere. This is a very serious thing. We don't pay attention to when we drive these petrochemical vehicles, but that is the kind of CO2 we are putting into the atmosphere. And with this kind of number of cars going be on the road, so it will contribute to a significant CO2 increase in the atmosphere. For this reason, every automotive industries are now shifting towards more sustainable mode of transport. So they are moving into plug-in electric vehicles or fuel cell vehicles, right? So every auto industries are in now they are more pressurized to make it to a electric vehicle, and this is a major program going on not only in India, in the globally, in all over, right? So these petrochemical driven vehicles should be converted into hybrid electric vehicle or electric vehicle, and for this application, the batteries are required. Batteries are the most suitable energy storage devices for automotive applications. Batteries will play a major role in this. Now, why batteries for the EV? There are so many other applications. If you look at the energy storage application, there can be different kind of energy storage, magnetic wheels, flywheels, or it could be hydroelectric storage, or there are different varieties of energy storage applications are available. Among them, batteries are the most suitable. Why for the EV? Why batteries? The simple answer is, if you look at typical gasoline-driven vehicles, the tank to wheel efficiency is just alone 13%. You can see from here, various losses happens from, for example, standby 8% of loss engine. So engine loss is 76%. Major loss happens due to these mechanical engines, right? You have 76% loss, then 17% the driveline. So totally the wheel efficiency is only 13%. Whereas in the battery driven vehicles, so the tank to wheel efficiency is about 80%. So from batteries, directly go to the motor. So motor will have a efficient conversion, is only loss is about 15%, and 85% is in the is efficiency in the driveline. So 80% efficiency could be achieved with if you are switching over to the electric vehicle. That is the reason batteries are considered the best option for EVs. So if you take these numbers, you have 6 times higher tank to wheel efficiency than the petrol or diesel driven vehicles. So that is the reason batteries play an important role for EVs. Now, all of you have heard about batteries, right? These batteries are not new. Batteries are not new. Batteries are there since, a lot of evolution happened. Just to give you an idea of how these batteries, whatever batteries we are using today, when did these things are done, what kind of evolution happened, you can see from here. So this concept of battery was demonstrated in 1780 by a French scientist Galvani. He was a kind of bio. He is a scientist working on the bio-related aspects. He was into human anatomy and and those kind of research he was doing. It was an accidental invention when he did first time when he saw this one. He was doing some kind of dissection of the frog. He accidentally touched the frog muscle with a copper and iron tweezers or rod or whatever. He saw that when he did that, he saw that the frog muscle was stretching. So that was the first observation of the concept of EMF or potential. That was in 1780s. Then that time he made a statement when a frog muscle produce electricity. Then after about another 30 years, another scientist named Volta, he has done the similar experiment, and what he did was he has piled up copper and zinc foils alternatively, and he separated those copper and zinc foils with a separator. It could be a piece of cloth or so, and the electrolyte he used, he soaked these cloth or paper in a salt water, and then he piled many of them, and then he showed the voltage across this cell. This is called a volta file. And then in 1800 he corrected the statement of Galvani. He said the frog muscle doesn't produce electricity. Electricity is produced when you come in contact, when you make the contact with the two dissimilar elements. The difference in the electrical redox potential is what it gives the voltage and so on. So that was the first demonstration of our concept of batteries, which have dated back to 17 or 1800 century. And this was the concept. And then later it is evolved, and further in 1836, Galvani, because one of the problem with the volta file is you have a production of hydrogen. When you are compiling these things, then there is a production of hydrogen on the zinc side, and which was acting as a kind of barrier. So in order to take care of that, Daniel has improved this concept of this volta file. What he did was he taken copper sulfate in one bath and zinc sulfate in another one, and he dipped a copper foil in the copper sulfate and zinc in zinc sulfate, and he connected these two through the salt bridge, and then you see a voltage across that. And this was the first demonstration of Daniel cell in 1836. That was a kind of cells which have come to an application and so on. And you all might have used these, in your +2 when you're doing. You might have used those Galvani Daniel cells. You have a copper part filled in copper sulfate, and then you use a kind of earthen part, and then the porous earthen part wherein you fill a zinc sulfate and you put a zinc rod and copper. So this was a Daniel cell, right? It gives you 1.1 volt or so. And later, then these primary cells comes into picture. Like, we are all use, right? We use everyday Nippon and these kind of cells. They are primary cells. They are essentially not rechargeable. Okay. So you can use these batteries as long as the charge is available. And later in you have secondaries batteries were invented. Lead acid battery is typically secondary battery. These secondary batteries can be recharged multiple times, like lead acid battery or nickel metalite, nickel cadmium and nickel iron batteries. All these are rechargeable batteries. So these things have evolved mostly on somewhere around the 1936 and so on. So these things comes into the picture. And until few years back, we all see, you might have seen in the camcorders or in the cameras or in other devices, they were using either nickel metallic or nickel cadmium batteries. So these batteries have a problem of voltage hysteresis or memory effect. When every time you have to charge this battery to the complete, if you have partially charged it or if you have partially discharged it, and these batteries will have a memory effect, and the next time they don't go to the same 100% charge state. This kind of issues were there. So these days no one uses these batteries. but there were like, until a few years, maybe about till 20 years back, these batteries will still exist. So of late, these lithium-ion batteries comes into the market. They were the leading batteries now for many applications. You all use lithium batteries. In your mobile phone has lithium batteries, and your all small handheld devices, etc., will have lithium batteries and so on. So these were the of late developments on batteries. When you talk about batteries, there are three important components comes into picture. Batteries inside the battery. The battery is an electrical energy storage device. Inside battery, you have three important components. One is a cathode material, another one is anode material, and then the electrolyte. Cathode material is a some kind of material which having the lithium, if it is for the lithium-ion battery, and electrolyte is the medium to conduct these ions, and anode material is the zinc or the material which can accept these lithium plus or so on. So these are anode material. And the voltage across these batteries are, voltage is nothing but the difference in potential between the two electrodes of a cell. I just want to fresh up your knowledge on what this terminal, where the voltage comes. So the voltage is the difference between the potential of two electrodes of a cell. Capacity in a battery is the total amount of electricity involved in the electrochemical reaction. We call it specific capacity. Specific capacity means 1 gram equivalent of material will deliver 96,500 coulombs or 26.8 ampere hour. So 96,500 coulombs is a charge on 1 mole of electron, right? If you convert into ampere hour, you divided by 96,500 divided by 3,000 seconds in 1 hour. So that comes to 26.8 is an ampere hour. Theoretical capacity therefore would be 26.8 divided by molecular weight of this, either the cathode or anode material. So that is in ampere hour per gram. Observed capacity would be how much of current and for how many hours or duration, current into time is the observed capacity. So in more detail about the anode, anode is the electrode at which the oxidation takes place and which gives up electrons to the external circuit. Cathode is the electrode at which the reduction takes place and which withdraws electron from the external circuit. Electrolyte is the medium which permits ionic conduction between the electrodes of a cell. They are the three important components in any of the batteries you take. Either it could be lithium or it could be zinc air or nickel metal hydride or anything. You have anode, cathode, and electrolyte, and these are the kind of reactions happens. These batteries essentially an oxidation reduction reaction, and the electrons involved in these oxidation reduction reactions will be utilized to the external circuit. That's how your whatever the current you see is a flow of electron coming from this oxidation and reduction of the materials used in those batteries. Now there are different types of batteries, right? I have told you where several types of batteries are available, and so which kind of battery to be used for what applications? It depends on your application, your requirement, especially for EV. If you are looking for electric vehicle, then which battery is suitable? Even among the recharge level batteries, you have a lead acid battery, you have nickel cadmium battery, you have nickel metal hydride battery, and then you have lithium ion and polymer lithium ion, etc. You see here, lead acid battery, you are all well aware, you all use these batteries in your UPS at home, for when the power goes up, you will all use these lead acid batteries for as a backup and so on. These batteries have a low energy density, has a low volumetric as well as gravimetric energy density. Gravimetric energy density is so much of energy stored per weight, per kg of the battery, as well as volumetric is energy density with respect to the volume. Okay, so in both these aspects, the lead acid batteries will have a lower energy density, which is typically about somewhere around 70 to less than 100, 70 to 80 watt-hour per kg or so on, or lead acid. Nickel cadmium has a little higher energy density than the lead acid. Nickel metal hydride is even higher energy density than these two. But however, these batteries have, as I said, there are a lot of drawbacks in terms of memory effects, voltage hysteresis, and so on. So those batteries may not be the best. And the lithium ion has a greater advantage because they are lightweight. You all use this battery, typically in your mobile phone may have 2 ampere hour to something like 3.6 to 4 ampere hour batteries are used in your mobile phone, right? So they are very compact. So the mobiles have become so handy now these days because of the battery. Otherwise, imagine if any other batteries has to be used, these mobiles would not have been so light and so lightweight as well as handy. They would have been higher. So due to these lithium batteries have possess an higher volumetric and gravimetric energy density, these batteries can be so compact and they can be useful for many of these kind of applications and so on. Even for EV, if you typically, let us say, use a lead acid battery for electric vehicle, like let us take for example, if you want to drive something like 60 to 80 kilometer in one charge, you are using 4-door electric car. Do you know what would be the weight and the volume of the batteries? The batteries would weigh more than the car itself, and also these batteries will have higher we will have the volume of these batteries would be almost the size of the car itself. That's the kind of thing if you want to drive. Now everybody is targeting something like 150 kilometer in one drive, one charge and so on. So none of these batteries will be suitable. Therefore, the lithium batteries could be only the best option to meet such kind of requirements and so on. When you talk about the lithium-ion batteries, there are criteria. It has to pass many things. These are the goals of lithium batteries. These batteries has to meet in terms of energy. These batteries should provide adequate range within weight and space constraints. In the car, you may have to place these batteries. You have a constraint of the volume. You have these batteries should be compact and so on. And similarly, the weight, the batteries should not be so much weight that it will the whole load will be coming from the batteries. So you have that, and so therefore you need to have an higher energy density for these batteries. And this is more important for plug-in hybrid electric vehicle as well as EVs or even for hybrid electric vehicles. And safety is another important aspect, because many of you know that lithium-ion batteries, there were some incidents. There were some incidents of. Would you kindly mute your mic? There were some disturbances. So there are incidents like, safety is one of the important thing. So sometimes these batteries catch fire and so on. So this kind of catastrophic damage should not happen. So the battery should be safe and so on. And then the life of these batteries. Typically, you need to have something like 15 years of calendar life. Because these batteries are expensive, and when you buy, at least you should be able to sustain for 15 years and so on. Cycle life. So if it is for hybrid electric vehicles, it needs a microcycles. Lifetime EV full cycle. If it is plug-in hybrid electric vehicle, both micro and full cycle lifetime is required. And the cost is another important thing. And this is one of the largest obstacle to the commercialization of both the plug-in hybrid electric vehicle or electric vehicle. Typically, the cost of these batteries are, let us say, take for example, there are some cars in the market which are driven with, which are lithium battery powered cars. The cost of these batteries are typically about 5 to 6 lakh rupees, depending on drive range and so on. So it could be even more for example, for about 60 kilometer range and so on. So the cost of these batteries itself is about 6 to 7 lakh rupees, which is expensive. So there are requirements that these batteries has to be cheaper and so on. And the power is when you accelerate, the battery should be able to give that kind of high boost when you are accelerating or when you are up hills and so on. So the battery should be able to provide adequate boost for HEV application, and this is less important for plug-in applications. So these are the various requirements, and the batteries are expected to give all these requirements. Many, as all of you, I think you know that, right? Last year, this year Nobel Prize was given for lithium-ion batteries. These are the three important people who received this Nobel Prize for lithium batteries. This is Professor Goodenough, and he is from University of Texas in USA, and this is Stanley Wattingham from UK, and he is a Professor Akira Yoshino, and he is a Japanese professor. Now, these are the three people shared the Nobel. This is a Nobel Prize for lithium batteries, and what they have done was, the first concept of the battery was demonstrated by this professor, Professor Wattingham. What he showed was he used a titanium disulfide. Titanium disulfide is a material which is a layered structure, which has a kind of layer structure. So he used this titanium disulfide and used a lithium metal, and then he showed intercalation of lithium ions into these titanium disulfide layers. And in this titanium disulfide, what happens is titanium disulfide is typically titanium is in 4+ oxidation state. Titanium metal is 0. Titanium disulfide is 4+ oxidation state. When you intercalate these lithium into titanium disulfide, you have a redox of titanium 2+ to 4+, and this happens around 2 volt. So by doing that, he showed the 2 volt across lithium metal and TiS2, and he showed this. This was the first demonstration of lithium in batteries. And then after about a few years, after about 10 years, Professor Goodenough has come up with another novel material. What he used was, instead of titanium disulfide, he invented a new material, which is a lithium cobalt oxide. Here, this is also a layered compound. Lithium cobalt oxide is also a layered compound, as a layer structure like titanium disulfide. And one advantage here is this cobalt in the lithium cobalt oxide, the oxidation state of cobalt is cobalt 3+. When you remove lithium from lithium cobalt oxide, it goes to 4+. So the redox of cobalt happens around this 3+ to 4+ happens around 4 volt. So just by changing the material, just by changing the chemistry or a material, he showed 4 volt across this. So 2 volt, the initial demonstration, now we increase the voltage up to 4 volt. Then one of the issues for certain time, the people were using lithium metal as one of the polymer electrolytes. They were using lithium polymer batteries. They were using lithium metal and polymer electrolytes, and they were using lithium cobalt oxide and things like that. So those batteries are being used. But one of the issue was lithium metal is very highly unsafe. Lithium metal is it's an alkali metal. If it comes in contact with water, or if it comes in contact with the air and so on, there could be explosion issues. So it's not safe and so on. So then this guy, Professor Akira Yoshino, he is a Japanese guy. He was working on he's a scientist in one of the petrochemical industry. He was working on different kind of carbons and so on, some kind of disorder carbons and so on. And what he did was, he has developed this, he used graphite. Graphite is a layered material. So he used a graphite-based carbon. Actually, first he was used a petroleum pitch carbon, and then he demonstrated lithium intercalation into these graphitic layers. And therefore, now you don't need to use lithium metal. You can just use a graphite. And when you oxidize it, when you charge it, lithium plus from lithium cobalt oxide will be intercalated into the graphite, and you see a voltage across. So this is practically these things become possible. It took almost now we all use lithium batteries so extensively, but the first demonstrations you can see here, it was 1970s. So almost in these 30 years, so much developments happened. So these were the beginning. And these three people have laid the foundation for these wireless electronics. We all use your mobile phones. We all use batteries for various applications, okay, for EVs and so on. Their contribution is highly appreciated, and it is very significant. This is a thing. It was in about 30 years back, and this led to so much of revolution in the electronic industries and so on. So this is the rechargeable lithium battery schematics of rechargeability, how it works. As I said, you have a cathode materials. Typically, the cathode materials are lithium containing transition metal oxides like lithium cobalt oxide, lithium manganese oxide, or lithium iron phosphate, wherein the structure should have either layered compound or the kind of 3-dimensional structure for lithium ion diffusion and so on. and then the negative electrode is graphite, and then these things are separated with the separator, which are soaked in the electrolyte. Electrolyte is typically non-aqueous organic electrolyte which conduct lithium ions. Okay, typically we use lithium hexafluorophosphate in ethylene carbonate or dimethyl carbonate, etc., as a solvents. So when you charge these batteries, your lithium is removed from cathode, and the electrolyte will transport it, and then it is integrated into the graphite. So this material is getting oxidized, this material is getting reduced. So you have the electrons will be utilized, moving around through the external circuit. So when you charge it, you from the lithium cobalt oxide plus carbon, you deintegrate lithium, and then you integrate into the carbon, and the equivalent number of electrons will be released from this reaction. Okay, when you discharge it, so the opposite of that happens, and you form back lithium cobalt oxide and carbon. So this is how it happens. So if you have to develop, like as I said earlier, specific capacity is calculated by, this is a formula we use, 26.8. I already told you from where this comes. This comes from the Faraday equation. 96,500 is the Coulombs on 1 mole of electron, and you divide that by 3,600 seconds in 1 hour. It is 26.8 is an ampere hour into delta X. Delta X is number of moles of lithium or electron involved in this reaction. For example, if you remove 50% of lithium from lithium cobalt oxide, then you have, this is 0.5, right? And the M is molecular weight of lithium cobalt oxide. It's about typically about 96, 97 or so. So that's here. So if you want to develop batteries, like for example, all of us are using now mobile phone. In one charge, we are using it for almost like 1 day. Okay. If you want to use it for a longer duration, if you want to have a more talking time with one charge, all that we have to do is we have to choose the materials which have which can either give you this more number of lithium exchange, or use the materials which have a low molecular weight. It's that simple. You have to devise, or you have to invent those kind of materials which can give you higher capacity by either they can give you more number of electron exchange per mole of compound, or it could have the lower molecular weight. It can also be used by increasing the energy density. You can also be used by, you can also increase it by voltage into capacity. Voltage, you can, for example, this is about 4 volt. So you invent a material which can give you 4.6 or 4.8 volt. There also you can increase the energy density. So these are the various concepts. If you have to develop a better batteries for various applications, we have to work on this kind of research and come up with the things. Now, as I said, lithium battery composed of is a combination of a positive and negative electrode, right? As I said, is an anode and cathode. Cathode is a positive electrode, anode is a negative electrode. So what that does, so in if you look at in the industry, there are several types of chemistries are there. You can use a graphite in combination with the lithium cobalt oxide, graphite in combination with the lithium nickel cobalt oxide, or graphite with the lithium iron phosphate, graphite with the lithium manganese oxide, graphite with the NMC, or alloy-based electrodes with the positive electrode, or silicon carbon composite. So like this, there are several compositions exist. If you see here, these are called half-cell reaction. Half-cell reaction means, for example, this compound you take, this is a lithium nickel manganese oxide spinel. Okay, so when we make a cell versus lithium, when you make a cell versus lithium with the lithium metal, you have a plateau like that. So you have a potential of about 4.6 volt, and the graphite intercalation potential is around close to about 0.1, 0.2 volt, right? So graphite capacity is about 375 milliampere hour. So just for the comparison and to see in a one graph, I just divide by half to reduce the capacity. So here the potential of graphite is here. So if you make a battery with the graphite in combination with the lithium nickel manganese spinel, then you see about the voltage of 4.5 volt, right? If you are making, let us say for example, lithium titanate is another anode material or a negative electrode material. If you are using lithium titanate versus the same lithium nickel manganese oxide, so this potential is about 1.5 volt. Then what happens? The difference between the potential of positive and negative volt is 4.5 volt minus 1.5 volt. So you get about 3 volt here. Okay. Similarly, so one can decide, for example, lithium iron phosphate versus LTO, then it is 2 volt. So depending on what kind of voltage, each of these cathode, anode, etc., depending on the application, one has to select carefully what kind of chemistry to be chosen, and what are the drawbacks of this chemistry, what are the positive aspects of this chemistry, etc. And then one can decide what is the combination they should do. You should use it for developing these batteries and so on. Okay. Now, these batteries, the lithium batteries, are available in several aspects. Like you might have seen cylindrical cell. They are of your everyday cell. Like you call it a 18650 cells or 26650 cells. They are 18650 cells. What we call is 18 mm dia, 650 mm height in a cylindrical cell. Whereas the cells used in your mobile phones are kind of prismatic. They are not the circular one, cylindrical. They are a prismatic type. They are called pouch cells, and there are prismatic cells. Like there are different provisions are there, either cylindrical, prismatic, or pouch cells, and small cells like button cells you also use in your watches and things like that. They are called button cells or coin cells. Okay, so they are available in different aspects. These batteries, there are several applications. In a very small batteries like few milliampere hour, they have been used in your laptops, okay, or notepad, or in your mobile phones, smartphone, notepad, tablet, and web devices. And for these kind of applications, we use a few ampere hour capacity, batteries which are typically about maybe 1 to 10, 1 to 5 to 6 ampere hour, or even up to 10 ampere hour could be used for this kind of application. Even the smallest batteries like thin film batteries, etc., can be used for other applications like convenience devices. It could be for sensors or smart cards or wearable or flexible electronics, e-paper. For those kind of application you can use, and the capacity of these batteries would be very small. They will be something like milliampere hour range, up to hundreds of milliampere hour. They can be useful for these applications. For when you talk about applications like automotive sectors or transport applications for EVs and so on, so the batteries capacity of these
Seems like sir has disconnected his page for some time.
Hello.
Yes, sir. Yes, sir. Yes, sir. You're audible.
Sorry, but there was a problem. I
Okay,
think
okay.
you lost the connection.
No, no. Our connection was fine, sir. I think your connection
Yeah,
was
no.
lost.
Here there was
Okay, okay, okay,
some
okay.
switchover of the electricity happened, and
Okay,
then I
fine,
lost
fine.
connection.
No issue, no issue, sir. This you
I
can
think
continue.
till because I was talking about applications, you all
Yes, yes,
heard
sir.
that, or before that it was
Yeah, during that time only, sir, it got disconnected.
okay. Fine. Yeah, I'll continue from that. So for EV application, up to few hundreds of kilowatts are useful for EV application. So the batteries are to be combined. You have to, one has to develop a pack with the combining various batteries to get the required current and voltage, and they can be used for this kind of electric vehicle application. So these batteries can also be, even still larger format, up to megawatt, gigawatts, etc. Can be used or find application for storage applications, like for example for storing renewables like solar energy storage or wind power storage, wind energy storage, or grid application. So the up to beyond megawatts, etc. scale can be they find application for this. So the smallest to the bigger thing, they would be useful for many applications and so on. So that are the kind of application of batteries. And these batteries, although these batteries are the commercially established products, still R&D is required to improve the performance to meet for EV requirements, and also enhancement in terms of safety, energy density, and cost are needed, especially in Indian context. For these batteries are we all right now there is no manufacturing. We'll import these batteries. So to suit our requirements, our Indian conditions, your geographical conditions, or even in look at your Indian customers' usage pattern can also be different. So the specifically for these kind of applications and keeping in target with that. So there are customization or maybe kind of R&D required to do to meet special requirements and so on. So that is the reason, and it's important that R&D and various aspects. Although it's a commercial thing, still there are a lot of things one need to do, and a lot of R&D goes on these aspects. So we basically, I'm a chemist. We work on developing a better batteries or building a better batteries in terms of looking at their structure. We look at the mostly on the scientific approaches, chemistry approaches into improve these batteries and to do to make materials which can either give you higher capacity or higher voltage or higher cycle life or a better safety. Okay, we manipulate many things, the compositions or the crystal structure or the properties of the materials, etc., by playing around with the chemical, with the elements in those compounds or in the structure and so on. There are these are the current status of materials. The cathode materials are concerned. You have lithium cobalt oxide, which was, as I said, that was the invention of Professor Goodenough. Still, this material is being used even till today, and this is a 4-volt cathode, and the capacity is 140 ampere hour per kg, and volumetric energy density is about 560 watt hour per kg. Here, only 50% of the theoretical capacity could be utilized, because more than 50% if you draw, then you have there is an inherent safety aspect with this lithium cobalt oxide. There is a more chemistry, the oxygen 2p bands will be overlapping with the cobalt 2p cobalt 3d bands, and then the oxygen will be destructured from the cathode material, and this lead to safety aspects and so on. And the cobalt is expensive as well as toxic, and this is mostly used for portable devices like mobile phones and so on, but could not be employed for EVs because of safety aspects, as well as due to the other hindrance, cost and other things. And spinel element 4 is also 4-volt lithium manganese oxide, and the capacity is 120 ampere hour per kg, and volumetric is 480 watt hour per kg. Manganese is very cheap, is inexpensive, and environmentally benign, is safe. Whereas 3D structure, it provides high power as well as safety, but however, it has a severe capacity degradation. If you want to use it for a longer cycle life, this may be good for something like if you are targeting for some application, if you are targeting 200 cycles or 250 cycles or 300, then you can use it. If it is for longer cycle life, it is not good, because every cycle life there is a decay in the capacity and so on. And another option is lithium iron phosphate is another cathode material. Use iron as an important resource. Other things are phosphate. Phosphate is plenty available. Lithium, and this cathode gives you 3.5 volt, and gravimetric energy density is 160 ampere hour per kg. Volumetric is 560 watt hour per kg. Iron is inexpensive and environmentally benign. And here you have a covalently bonded PO4 groups. It offers excellent safety. These are expected to be higher safety than either lithium cobalt oxide and MC, etc. And it has one issue is it has a low electronic conductivity. Therefore, there is a big polarization, and then the rate performance, etc. were the issues. There were people follow different kind of strategies to overcome those drawbacks and so on. And on the anode side, mostly used commercially is the graphite-based carbon. Intercalation potential is 0.1 volt, and energy density is 370 watt hour per kg. It's inexpensive and environmentally benign. And so one of the issue is undesirable solid-state electrolyte interface layer.
It seems like there is a connectivity issue. I'll just wait for some time.
Wait.
Hello? Hello?
Yes, sir. Yes, sir. Yes, sir.
Sorry, there was, due to this cyclone, there were a lot of issues with the power disruption.
Okay, okay. So no issues.
Yeah. Yeah. So these are, as I said, there are different technologies, major reliability challenges and characteristics. As I said, there are different cathode materials are being used. So here, this chart will give you various characteristics. For example, as I said, in cathode materials, lithium cobalt oxide, lithium manganese oxide, lithium iron phosphate, lithium nickel cobalt oxide, and lithium nickel cobalt aluminum oxide. These are the 5 or 6 different cathode materials mostly used in all lithium-ion batteries, right? So how will you choose which chemistry to be used for what application and so on? So let us take here. The first one is for lithium nickel cobalt aluminum, or called NCA. So if you look at it here, it has a higher specific energy, it has a higher specific power, but safety is not good. You have less safety, and the performance is moderate, and the lifespan is also moderate, and cost is lower. So whereas it has this kind of characteristic. Whereas if you, so depending on your application, one can decide how you can select it. Let us look at it NMC. If you see NMC, specific energy, specific power, safety, reasonably it has most of the things it qualifies. NMC chemistry qualifies most of the things. Lithium manganese oxide, it is not good. Cost is cheaper. Our lifespan is also not good. You have, as I said, is only for low cycle life and so on. So therefore, lithium manganese oxide cannot be used, and performance is not good. And lithium iron phosphate can also be a good option, but whereas cost wise is moderate cheaper. Performance is, as I said, it has electronic conductivity issues and so on. But whereas specific energy is lower. So these are the different these are the things, and depending on application, one can choose the required chemistry for using for the application. If you look at commercially, there are several industries worldwide making lithium-ion batteries and supplying, right? So lithium iron phosphate versus graphite. So A123, BYD, Amperex, Lithium. These are the companies, leading companies who are making, who use this chemistry. And capacity ampere per gram is 159. Energy density is 85 to 105. Lithium manganese spinel, LMO versus graphite, is capacity is 120 and energy density is 140 to 180. LG Chem, ACS, Samsung, SDI, etc. use this. And lithium cobalt oxide, again, Samsung, BYD, LG Chem, Panasonic, Alta, Lithium, these companies use it. Lithium titanate versus LMO, ATL, Toshiba, Leclanche, Microvast, these are the companies. So you can see here, the energy density can vary from 85 to somewhere around up to 200 watt hour per kg. Lithium cobalt oxide or NMC. Here NMC you can see they can go up to 200 watt hour per kg. So there are things, and the cycle life is there. So which battery will give you better cycle life and so on, and the price also are given. So the cost, depending on what kind of materials you use in the battery, cost can vary. It can vary from 240 to up to 900 to 2200 kg per so on. So there is, as I said, in SICRI, we are working on several materials. One of the materials which we would like to talk about is NMC. You might have all heard NMC chemistry, batteries based on NMC chemistry and so on. NMC are the most used is the most used cathode material in lithium-ion battery. So, and in these NMC there are various variants: nickel, manganese, cobalt. So NMC means nickel, manganese, cobalt, and 111 NMC 111 means nickel is 1/3, manganese 1/3, cobalt 1/3. So these numbers, NMC 442 is nickel 40%, manganese 40%, cobalt 20%. NMC 532 is nickel 50%, manganese 30%. So like that, there are different compositions can be arrived at it, and these compositions will have their own characteristic in terms of thermal stability, in terms of voltage, in terms of capacity. They have their own discrete characteristic in the performance and so on. So these are the various chemistries one could use it. And so NMC, as I said, this is a layered compound. If you are most of you are engineering, I'm not sure how much you can understand the structures and chemistry and so on. In a nutshell, I can tell you these are layered compounds. Layered compound means these 3D metal oxides, nickel, manganese, cobalt forms an octahedra. They are all corner and edge shade octahedras forms a layers, and lithiums are located in between these two layers. Like that, they have a kind of compounds. In this material, one of the challenge is to occupying nickel with the lithium site, and that can give you kind of rate performance and issues and so on. how one can arrive at this kind of cation disorders and so on is a challenge. One work with the synthesis of the material and so on. So we have technology for the production of NMC, and we have developed these various compositions of NMC in our lab, and we scaled it up, and these are the performance characteristic of those NMC. They were on par with the commercial materials which we import and so on. So they can be used and they have a very good performance. So they can give you kind of benchmark of performance comparable with the commercial materials and so on. We use them in laboratory. What we do is our whole research is translating the laboratory innovation to the prototype products. We start from using the chemicals to make the materials, and then synthesize the materials. Once we synthesize, once we assess these materials in a small cell level, then we scale it up to few grams or few kgs of level, and then produce these prototype cells. Like these are called pouch cells. These are all cylindrical 18650 cells. So this is the kind of activity we do here in our lab. So we do research on various new compositions, new materials, or materials with improved properties and so on. So that's the kind of things we do. And we have a capability and facility to fabricate or manufacture both the cylindrical as well as prismatic cells. And what we buy is chemicals and the components like aluminum, copper foils and separator, and other accessories like cell cans and so on. Use these materials and we'll develop the material. And we have a technology for production of lithium batteries, and use these batteries to make cells. And here the typical, once we make the materials, then there are a lot of engineering is involved. The whole process is a whole kind of chemical engineering, mechanical and electrical engineering stuff. There are a lot of processing things we have to do. So the cathode material, once we develop, these are all in the powder form. Then they have to be converted into kind of viscous slurries by blending with binders and solvents and carbon and so on. And then they will have to be fabricated into the electrodes. So, we have to coat them onto the copper or aluminum foil and dry. There are several unit operations happens. So maybe about 23 to 25 unit operations happens, one stage to another stage. Each of these processes has to be carefully controlled to get the required performance of a cell and so on. So these are all what we have developed in our lab. And these are the various processes involved. These are the machineries. So the mixing initially, the cathode, anode materials, cathode slurry, like mixing with the carbon and the binder, etc. Or then we call it a slurry preparation. And then they are coated, and then they call it a calendering process, wherein you compact the electrodes, and then the electrodes has to be slitted or cut into the particular dimension. That's called slitting process. And then the notching is the electrode dimension, the cut into the electrode dimension, and then the vacuum drying. And so these are the various processes one has to follow to fabricate lithium-ion batteries. We have developed, we have a complete machineries, like this is a kind of electrode slurry machine, wherein we can take all these powdered raw materials, and then we put into these machines, we blend it with the electrolyte, we blend it with the solvents and so on. And this one is the electrode coating machine. So at one stage, we can coat something like up to hundreds of meters of length of aluminum and copper foil can be coated with this electrode slurry, and we have all these machineries. And then this is called a calendering process. In this process, to get the required energy densities, the electrodes has to be compacted. The higher the compaction, the better the energy density you could get. Is a kind of compaction with the heat, and then the whole batteries has to be fabricated in a controlled atmosphere. Batteries are the electromaterials or electrolyte are very sensitive to moisture. The kind of atmospheric level we need is we have to fabricate this whole battery at minus 60 degree dew point or less than 0.4% humidity level. So this is a kind of, we call it a dry room. This is a kind of facility we have. Each of these machines are used for particular operations. As I said, 23 to 25 unit operations are there. Each of these machines does a particular operation, and then we make batteries. So these are various other machineries required for fabrication. And we make this kind of 18650 cells, and this specification of cells we prepare. So the batteries we prepare in our lab are about 2.5 ampere hour and 3.6 volt. And these are the charging conditions. Weight of these batteries are 46 degrees. These batteries can be used at temperature for 10 to 55 degrees centigrade, and discharging is also 10 to 55. And storage can also be done up to 10 to 55 degrees centigrade. Energy density is about 512 and gravimetric is 195. So these are the specification of the cells we prepare. As you can see here, just to give you idea of where do we stand, I give you the bottom one was a cell from Samsung. So they are about 45 grams and 3.6 volt and 2.5 ampere hour. Presently with NMC similar chemistry, we have reached a capacity of 2.3 ampere hour. So energy density is 192. So we are almost there to the commercial level, volumetric is 470 and this is about 526. We are almost there, and some other chemistries we are able to meet the benchmark of commercial cells from LG or Samsung or wherever. And we have used these cells, whatever we developed in our laboratories for various applications like consumer electronics, to have a either could be torch light, rechargeable torches, or could be solar lanterns, or even for power bank applications, or even for EV. This was last year, last December, our Minister, Science and Technology Minister Harshavardhan, when he visited, he has used this EV with our lithium battery powered two-wheeler scooter. So we demonstrated to him, and he took a ride. And this was the indigenous lithium batteries developed from our lab. And this is a DG CSR, Director General of CSR, Dr. Shekhar Mande. So this was he took a ride with our EV, and this was electric bicycle. And for this we have used I think 1.2 kilowatt battery pack for this vehicle, and we also demonstrated for solar street light applications and so on. So these are the various demonstrations we conducted using our indigenous cells. If you consider lithium batteries, there is a big demand for lithium batteries in India. These are one of the statistics from Niti Aayog. You can see here in India, by in about 2030, you will have about 200 million two-wheelers. So even each two-wheeler require 1 to 2.7 kilowatt hour. You need the total kind of battery requirement, if you see, is about 200 to 540 gigawatt. And four-wheelers about 40 million. So four-wheelers will need about 10 to 20 kilowatt hour. So that again, 400 to 800 gigawatts. And for buses is about 300 to 970. And these batteries are also required for energy storage, which would be about 22 gigawatt hour. So even if there is a small percentage of 30% penetration, the requirement for batteries is a huge. And right now there is no Indian industry manufacturing batteries. So there is a lot of demand to improve the technology and to develop this, use this indigenous technology, because many of these technologies are owned by international companies like Samsung, LG, BYD, and things like that. So it is important for India to develop our own technology and to have an IP rights and so on. In this direction, we work towards that. And if you look at the opportunities, it's a multi-billion dollar lithium battery industry, provide economic growth for the country. It provide economic opportunity for lakhs of laborers and skilled laborers, and complete electrification using lithium battery storage technology for rural India can provide you better quality of life. Making in India as one of the main player for energy storage, competition by having self-sustained manufacturing facility of lithium battery, huge impact on electric vehicle industry by reducing the fossil fuel consumption and providing pollution-free environment. And then digital campaign has resulted in revolution in electronic industry where the lithium battery storage system plays an important role. So these are things. So what we do at SICRI, we have recently, government has awarded a mega project to set up a facility for 100 mega production of 100 megawatt lithium battery production. So I just got the recently funding for about 100 crores for putting up this 100 megawatt plant, wherein we work with several industries. We do kind of handholding. It could be including raw material industry, refinery, material refining industries, and use these materials to develop anode, cathode, electrolyte. There are a lot of business opportunities. We work with several industries on various components and to produce the batteries and to produce battery packs and so many things. So there are kind of things. So and what we are trying to do is to create indigenization platform. We work with several industries. For example, for cathode materials like Tata Chemicals, Carbon and Amino, there are a few companies working with us, and we partner with them, and they have taken the technology to make those materials and so on. So we identify what these companies can do and what we can do to help with them, and coming up with India's own requirement for various components and subcomponents of these batteries and use these batteries for application and so on. So these are our industry partners whom we work. Our technology roadmap, right now we have developed these NMC 532, 622, etc. We are here at 2020. We are presently at 111 and 532 chemistries we have now. So these are for the future NMC 81, etc. They have higher energy density, but there are a lot of R&D required and so on. So presently we are at here. We are working with the NMC 532 technology for various applications and so on. Okay, so in this EV roadmap, we are somewhere in the beginning. We are demonstrating in the pilot level, and battery technology has been developed in the pilot level, in the pack development, etc. We work with industries as well as our own indigenous cells are used for many applications. So on. We are somewhere here in this thing. Yeah. In summary, India's requirement for batteries is huge, and no Indian company is making the cells as of now. It is a big opportunity. It is possible that Make in India batteries be cost competent than the imported cells from China, Korea, Japan, or elsewhere. If we create supply chain for indigenous raw materials and component, scale up possibility to develop NMC cathode system to improve the energy density, power, and safety, and to reduce the cost. And also there is a threat of not getting the quality cells or guaranteed availability if we depend on cell import, especially for strategic applications like for militaries and so on. So it is important that in India these batteries has to be developed and the technology to be developed, and then many industries should manufacture batteries and so on. So SICRI work in these directions to meet India's requirement for meeting some of these details. Thank you. Yeah, I would be happy to answer if there are any questions from.
Yes, sir. Thank you very much, sir. I think we got some questions in the chat box. I can pick up. Okay. One of the participants mentioned about lithium polymer battery. I don't know during which particular slide he or she had mentioned. Lithium, sir, is lithium polymer battery.
Okay. On the what do you want to know on the lithium and polymer battery?
Yeah. Pawan Kriti, can you just speak up because the question is not clear.
Hello, can you hear me?
Yes, I could hear you.
I am Dr. Saravanan. What about lithium polymer battery? It is weighs less than the lithium ion, no? So
Okay.
what about the future? Is there any problem with lithium polymer compared to lithium ion?
I just want to clarify you one thing.
Yes,
whatever the lithium polymer batteries earlier, a few years back, which you are talking about, were actually they were using a polymer electrolyte and a lithium metal. Now, no more those kind of cells are used. Now, whatever the industry convention they use lithium polymer is for the pouch cells. They are also lithium-ion batteries only. Only thing is the cell encasing is done with the polymer pouch. I have told you. So that is the thing, and they've been used for EVs and so on. Depending on application, one can decide on that. So as a structural stability compared to those hard stainless steel or prismatic, lithium polymer batteries, because you have to use a polymer pouch instead of stainless steel case. So if you are taking care of those issues that these batteries are not exposed, etc., it is fine. In terms of energy density, like you use the same material, same anode, cathode, electrolyte, etc. So the all that gain you could gain in the lithium polymer pouches, polymer batteries are the pouch, that lithium pouch you use, the polymer pouch is having a low weight compared to the either aluminum container or steel container. That's all. So energy density can be marginally higher. That's all.
Okay, sir. Okay, thank you, sir.
Thank you. Yes.
Another question I could see from the chat box is what is the safe way to dispose of the conventional pencil battery?
Safe way to dispose would be if the batteries are having some reasonable life, best is to discharge it and then dispose it. Okay, and there is no way you can as I said, completely discharge it and dispose is the best way, and you cannot retrieve the material. Now there are recycling options are coming up. These batteries in a large quantity, we will several gigawatts of batteries will be utilized, and these batteries will be dumped. So there are options, because this is again a circular economy. People are looking at using these materials, recycle it and use them, etc. So those kind of things are happening. And maybe after a few years, no, you will have these batteries. Nobody will would just throw them into the garbage. They would be depositing, or maybe some markets will be buying them back, buyback, or something like those kind of things would happen. Especially for large scale, EV batteries, etc. For small cells like mobile phones, etc., they are small batteries. It may not be an issue. It may not be issue. But for bigger things, those kind of recycling, etc., there were things are happening. Maybe it would take few years, so it would all happen. Yeah.
Okay. Another question, sir. I think following the same question, the same person is asking how harmful is considerable if the charged battery.
Yeah, I got it. I saw this. So yeah, as I said, these are all as I said, in the battery you use carbon or lithium, nickel, manganese, cobalt, etc. So an environmental aspects, if you see, these are all like nickel, manganese, cobalt, etc. are there in the steel also. So if you are disposing the steel to on the soil, once they corrode on these things. So I disposing to the ground, etc. may not be issue, but what we call, they are not toxic like other materials. Cobalt is toxic, but unless somebody consume it and so on. So as long as they are there in this one, it's not a problem. As I said, there are things are happening due for the recycling and so on. Eventually, those things will be in place after a few years. Right now, it is too premature to talk about the recycling. However, few companies are there, unless somebody has a large quantity of batteries, etc. But since our requirements right now are not so much, people are not bothered.
Okay, thank you, sir. And another question is regarding the battery optimization, sir.
Yeah.
What are the criteria for battery optimization?
I don't know in what context you are asking optimization. Optimization, is it like for example, for the pack development, you cannot use the batteries of the different SOCs. One has to bring down these batteries to a same voltage or same internal resistance, then combine together. Is this the kind of automation you are asking, or is it in a different context?
Zia Muhammad, you can speak up if you want to clarify the question.
Yes, sir.
Okay. Yeah. If you are in the pack development, if you are asking, so what do they do is there are, like, for example, if you are making a 10 kilowatt system, then you have to combine almost like 1,000 or something like thousands of batteries, right? So
Yes.
how do you optimize it? One has to do a screening they will check the internal resistance, and then you have to use batteries with the same internal resistance and with the same kind of SOC. That's called grading. One is to check the internal resistance and group them together with the same internal resistance, and then you could use it. That's the way to optimize it. And then you also grade them, like, all of them. If you are using for packing, if you are using all of them at 40% SOC, use all the batteries at the 40% SOC. If they are a different state of charge, that is not good. So these are the two things one need to take care.
Okay, sir. Thanks a lot, sir.
Another question coming from Udaya Kumar RK regarding the LIV for heavy vehicles, sir. What will be the torque?
Vehicles. Yeah, what is the torque required for heavy payload? Yeah, it depends on the. I am not an electrical engineer, but what I could say is even for vehicle, one thing what happens is any motor, if you take initially when you switch on, there is a lot more power requirement. It draw more power than it is normal application. Let us say, for example, we work with a strategic application for Air Force and things like that. No, so even for aeroplanes, they use these batteries for defense application. These motors, no, they may take it up. For example, normal range, they may be using 50 ampere hour, but during the start, the torque required is huge. So the same 50 ampere hour for a fraction of milliseconds or microsecond, it can go up to 2000 ampere hour. So that is the kind of thing. The transit current can be high. Okay. So the batteries, most conventionally, most of these lithium iron phosphate based or NMC batteries would be able to give, because this is only for a few microseconds, and most of these packs will be able to give for this kind of, even for heavy vehicle application. It would not be an issue.
I think that answers, I think, his question. Sir, from my side, I have a couple of questions. Sir, first thing is regarding the safety issues that you're taking care of while carrying out any research. Sir, because as a means we are not people from the chemical background, so we do not know what is going on exactly inside the battery. So like we are actually, as a common people, we are scared of like means the battery may get blasted. Means if the capacity is higher. So how do you like clarify this kind of panic inside the common people?
Okay, yeah. There are primary safety done with something called BMS, okay, battery management system. There is a small circuit, electronic circuit. What it does is, when does the battery explode? When does when you abuse the battery, then only. So battery explosion, etc., are linked to the thermal issues. You know, when you are charging, discharging it with a very higher rates, the battery is getting heated up. Okay, when the battery is getting heated up, there is an organic electrolyte you use. They form a huge volume, you know, because organic electrolytes at that temperature, if you above 65, 70 degrees centigrade, there's a volume expansion of these organic electrolytes. They becomes vapors and so on. So those leads to the safety issues. One thing is, one will take care of, if due to those things, normally there is all thermal management which takes care of maintaining the temperature of these battery packs. Okay, BMS takes care of the limitation of the upper cutoff potential and lower cutoff potential. For example, beyond 4.5 volt, if you charge the battery, you know, you are charging it to the higher extreme. Then, as I said, let us say, for example, lithium cobalt oxide, you could, I told you, up to 0.5, 50% of the lithium, you could extract it. More than that, the safety issues come. So what happens is, this battery management system will limit the potential. Above 4.5 volt it goes, then it will stop the cell from charging. Okay, so you cannot charge more than 4.5 volt. So those are, one level is BMS, battery management system, it takes care of it. Other thing what I'm talking about is the thermal management, to take care of the safety, like, you know, to not allow these batteries to heat it up and so on. Second thing. And the third thing is inherent safety, how to develop the batteries with the safer batteries. Use electrolytes which are not flammable. Use materials which can be having a better thermal parameter, thermal characteristics and so on. Those kind of things. At different level, these things can be handled.
Sir, another question was, sir, is there any possibility like getting short circuited inside the internal of the batteries? Because short circuiting is a very like it's a dangerous issue.
Yes, it could happen. Yes, it could happen. It could happen. There were, I did not go into details today. See, when I said the negative electrode is a carbon. Okay, so let us say, for example, when you are charging and discharging batteries at a higher rate, then these lithium will not have sufficient time to go and intercalate into the carbon layers. Then they could be deposited as a lithium metal, and these lithium metal would grow as a needle. You call it a dendrites. It's a kind of growth. Once it lithium metal deposits, it grows as a needles, and it goes through the separator. And when it touches the other side of the electrode, that brings a short circuit. And the moment the short circuit happens, the moment the dendrites touch the other side, you have a short circuit. Short circuit lead to the transient temperature, or the heat, or a spark, and then you have an organic electrolyte. And these organic electrolytes, some of them will be decomposed form and so on. There will be combustible gases which can explode or which can catch fire. So those are the issues. There are different ways to tackle it. As I said, one is to material aspect, you know, to work on that, or the electrolyte, or the separator. There are strategies are there, various strategies to encounter that.
Okay. Okay, sir. That means the formation of these dendrites will take time. It is happening over the period of time, right, sir? Or
it happens. No, it happens over the period of time. As I said, the dendrite formation itself is linked to your negative electrode carbon. It might link to your electrolyte also. It also linked to the combination of positive and negative electrode. Let us say, for example, if you are using lithium titanate potential is 1.5 volt. Dendrite could never happen. Whatever the rate you use, even at whatever faster rate, etc., dendrite will not happen because the dendrite formation happens at the much lower potential, near to 0 volt, the lithium metal deposition. So in those ones, that is why lithium titanate based battery, although it is energy density is very, very low, it's about something like 50 watt hour per kg. But for strategic applications or for a very crucial application where safety is very important, one can think of lithium titanate based batteries. And these batteries life cycle, if you see, they can be up to 15,000 lives, 15,000 cycles also. People are talking about, demonstrated. 15,000 means almost like, how many years you can use? You can use it maybe 30, 40 years also. So those are the kind of things. So there are things in multiple ways one can handle.
Thank you very much, sir. The last question, but it is not related to lithium ion battery. Sir, what is the latest technology regarding the metal? Someone has written metal air battery, and these are super capacitor. I think, sir, you have.
Yes. Yeah, we do research on lithium air batteries, which have almost 10 times higher energy density than the lithium ion batteries. But however, as I said, these are all in the initial stage. We are all, we publish papers on that, etc. They are all in the very, those states. They have not come up to the level of commercial application. We still don't know how to make those kind of into a product or application, we can demonstrate a small cell, the lithium air batteries, if you see, energy densities are as good as petrol, you understood. So if it is a lithium air battery capacity could be about, so this is about 250 watt hour per kg, the state of the art now, whatever we reached, okay, 250 watt hour. So lithium batteries can be about up to 3000 watt hour per kg. You can imagine, one charge, if lithium air batteries happens to be in the near future, in one charge, you can almost drive like something like 1,000 kilometers. That can be, that is why though a lot of research is being done, a lot of activities are going on, but it takes time, there are a lot of issues to be sorted out, and the technology evolution, there are a lot of developments has to happen. It may take several years.
Thank you very much, sir. I think that's the last question, and thank you very much, sir, for finding time for us. And I think you are very busy all the time, but still you have given us time. So I'm very much thankful for the valuable session, and we got to learn so many new things on the battery, lithium-ion battery especially. And looking forward to see you in the future also, sir. Thank you for joining.
Thank you.
Thank you very much, sir. Participants, thank you very much for joining, and I think this is the last session for today, and we are concluding now, and we still have 7 minutes time to get the attendance link. The attendance link will be generated automatically in the Google Classroom, and it will also be sent in your registered email ID. So I cannot share the link right now because it will be generated automatically, so it will be coming. So have patience. Once it is generated, I think I will also be able to share it in the WhatsApp link also. Okay. So thank you for joining us, and for today, this is the I think last session. So we are concluding here. Thank you very much. Thank you. So tomorrow again we will assemble here at 10 before 10. You please join 10 minutes before 10 a.m. So tomorrow we will have a session on the electric vehicle policy. Which will be given by Dr. Rajesh Kumar Panda. He is serving as a manager in Power Grid Corporation of India Limited under this Smart Grid department. So he'll be giving lectures on the various policies and implementation processes. Okay. So I hope we'll be learning lots again from him. So see you tomorrow again. Thank you. Thank you very much. And the link will be different for tomorrow, and it will be again generated in the morning itself. Thank you.
Thank you, sir. Thank you, sir.
Thank you, Ali, sir.
It was a very informative session, sir. We have learned a lot of things about these batteries.
Thank you. Thank you, Dr. Ali sir from NIT UP.
Yeah, thank you, sir. Yes, sir.
Thank you very much.
We are expecting tomorrow also we are same